Boa tarde a todos. Eu queria agradecer a presença de todos aqui nesse nosso último colóquio do ano. E essa edição está acontecendo numa terça-feira, normalmente é na sexta-feira, então eu queria agradecer a presença de todos. Queria dar um agradecimento especial para todo o apoio institucional que a gente está recebendo para a realização do colóquio do IME, e em especial para Cris, Rose, Fred, Sérgio e Aguinaldo. Nosso agradecimento por ajudar com toda a organização do colóquio. Eu vou passar a palavra para a Márcia, que vai apresentar a nossa palestrante de hoje. Obrigada.
Bom, boa tarde a todos. Eu agradeço a presença. É uma satisfação apresentar a professora Ying San. Ying terminou o seu doutorado em 2011, na Texas A&M University. Agora ela é professora associada de estatística em KAUST, que é King Abdullah University of Science and Technology. The nickname is KAUST, em Arábia Saudita. E ela é líder do grupo de Environmental Statistics. She is in the PhD program. She advises many postgraduate students. And also the main area of research of her is estatística espaçio-temporal, com aplicações em ciências ambientais, box plot funcional, deep learning, machine learning, geoestatística em large dataset, e that's it. Sorry for change, for mix the Portuguese and the English. Okay. Welcome, Ying.
Totally understood.
You understood.
Try one more time.
Say something.
Hello, can you hear me? Okay, yeah. Okay, thank you. So I wouldn't repeat, just want to thank myself again. Okay, so I joined KAUST 2014. I think I've been in this department only once. I remember I gave a presentation on large data set using approximation method to solve the Gaussian process, to fit a Gaussian process to large spatial data set problem. This is basically the same problem, different solution. So my research mainly focuses on spatial-temporal statistics and environmental applications. I'm not an expert in machine learning or deep learning, but this is one project actually my students encouraged me to learn. So I will show you as my learning process, how did we approach this problem? Because 4 or 5 years ago, we knew nothing about the machine learning, deep neural networks. And one of my students, he said he really wanted to try one project in deep learning. So that's why we proposed this project. And now, after 4 or 5 years, we had a few projects along this line. So as you know, I'm running a research group on environmental statistics in KAUST. Environmental data often very big in size and complex in dependency. They are typically spatial-temporal observations, and they exhibit complex dynamics at different spatial-temporal scales. Traditional methodology may face many challenges. For example, the process itself may not be Gaussian. Then this best linear predictor might not be the best predictor anymore. And also large-scale spatial-temporal prediction raises computational challenges. So today I will present basically 2 papers. The first one is going to appear on Statistical Sinica. It's called DeepKriging. It's a spatially dependent deep neural networks for spatial prediction. Then the second one actually appeared a little bit earlier than the first work, is an extension for DeepKriging to space-time setting. So spatial-temporal DeepKriging, I will talk about spatial interpolation and in time, the probabilistic forecasting. My co-authors are two former students, Wan Fangchen and Yu Xiaoli. Both of them now are AI engineers in Bosch, in China company. So I think because of this research experience, it gave them a way to actually to enter this AI research. They also taught me to be open-minded, because it's really a new topic for me as well. And my collaborator, Brian Rich from NC State. Pradik Naik was my last PhD student. He defended his thesis in May. So one of his committee members is actually from computer science. At the end of the defense, he made a comment, says, I feel very refreshed to see the application of deep learning in spatial statistics. So that's also kind of encourage us to do more research along this line, actually in the intersection between machine learning, deep learning, and the spatial statistics. Okay, so this is a book I read to my sons. They really love it when they were little. This neural network, at that time, during pandemic, I found a series of books for babies, neural network, even quantum computing. They use very simple language. You see, they use the passive pairs. So there's an input layer, hidden layer, and an output layer. So nowadays, we talk about deep learning. That means we have multiple layers in between. Why deep learning? Because my expertise is in spatial statistics. In geostatistics, Kriging is commonly used for spatial prediction. So Kriging is the so-called best linear unbiased predictor. The features of Kriging prediction include it involves modeling the mean and the covariance functions of spatial process. Basically, it's conditional mean of a Gaussian process. Use conditional mean as a point prediction. Some drawbacks of Kriging prediction include it typically not optimal for non-Gaussian data. So suppose the best predictor is a nonlinear predictor. So Kriging cannot give the nonlinear prediction. And also it involves the classic decomposition of a large, dense covariance matrices. So computationally expensive for massive data set. On the other hand, deep learning provides a computationally scalable methodology for a variety of data types and a nonlinear prediction. So that gives us an idea, can we actually use the deep learning methodology or algorithm to help us for spatial prediction? So that's one of the motivation. So as I mentioned at the very beginning, this deep neural network here, I give a illustration of neural network. When we talk about neural network, we have an input layer and a hidden layer and output layer. When we have multiple hidden layers, the network becomes deeper and deeper. We call it a deep neural network. So in my talk, I will use DNN to denote deep neural networks. So for spatial data, the thing is difficult. One thing is difficult is the spatial dependence, because many machine learning or deep learning algorithms are designed for regression problems. So they don't explicitly consider the spatial dependency in the data. So here is one attempt to introduce spatial dependency in the neural network. Here, during our research, at the beginning, we tried many different ways. The results were not very good. Then we start to think why classical deep learning method cannot be directly used for spatial prediction. Because in real applications for spatial prediction problem, typically observations are spatially sparse. For example, if we have a monitoring network, like the sensors to monitor air quality or temperatures, typically they are sparse in space. And usually we consider spatial temporal data set. We don't really have a lot of replicas to train the data. Nowadays, many deep learning algorithms, they are trained by a lot of images. So if you can think about spatial data, typically it was thinking we also have a lot of images. But the difference is for deep learning image-based algorithms, they need a lot of training to train the algorithm. So here we only have one or few replicate spatial data can be collected. And also, typically, we don't have many covariates. This is so-called features in machine learning literature at the unobserved locations to help us to do the prediction. So the last one is the most important thing. Typically, processes exhibit spatial dependence. So how can we consider such spatial dependence in the neural network is a problem. So our first research goal is to develop deep learning-based methodology suitable for spatial prediction. So another direction is about forecasting. When we have space-time data sets, typically we have two goals. One is interpolation. Typically, you want to do spatial prediction at these unsampled locations. So forecasting is for the extrapolation for the future. So we need special treatment for this extrapolation part. Also, the machine learning and deep learning traditional method, they don't consider uncertainty quantification very much. Although these days, many research focus, they start to think about how to quantify the uncertainties. So for the forecast, we want to have a point forecast, and also we want to have these uncertainties. So we call it probabilistic forecasting. Basically, instead of point forecast, I want to have a predictive distribution conditional on the past observations. So we want to develop a framework that can offer probabilistic forecasting for space-time data. So that's the second goal for developing a deep learning-based methodology for probabilistic forecasting. So this page is a little bit dense. I'll go a little bit slowly just to clarify the notation. So DNN is a deep neural network. S0 means a new location. We don't have any observation, S0. So I want to predict the value at new location S0 based on all the observations. Z is a vector containing all the observations in n locations, S1 to capital N. And this F is a function learned by deep neural network. So this theta hat here are the parameters in neural network. So those are the bears and the weights, all those parameters. And this little x here are the covariates. So for example, if you want to predict air quality at one location, so those small x could be temperature, wind speed, wind direction, and those covariates. So here, this theta are the parameters in the deep neural network are estimated or by training. We pick which parameters can minimize the loss function. This loss function minimizes the observation and these function values. So this is a training process. In statistical language, is an estimation procedure. So estimation equals the training of a deep neural network. So once we train this deep neural network, we plug in the new covariates at a new location. We get output. That's our spatial prediction. So in the literature, traditionally, the one way to use the spatial information is to add covariates or coordinates as additional features to consider this location informations. So instead, in addition to all covariates we have, we add longitude and latitude at each locations as the input. But the problem is the deep neural network estimate one of these functions. This function is going to be a very complex function over the longitude and latitude at a new location. So this may take a huge effort to achieve a good approximation. So what we want to do is, can we do actually a little bit better to use the spatial information or to consider spatial dependence? Okay, so in geostatistics, Kriging, as I mentioned, is a best unbiased linear predictor. So basically, if you have a mean, this universal Kriging has this form. This sigma here is of size capital N by N. So that's the number of locations we have observations. So this sigma has the covariance between all the observations. So when the number of locations is large, this part we need to use collective decomposition. That's why computationally is expensive. So the motivation of deep Kriging is, in statistics we know if this spatial process can be approximated by a finite weighted sum of basis functions. So here, these phi are the basis functions in space in 2D. In my mind, it's a little bit similar to non-parametric function estimation, because if we have a 2D space, you put on spatial basis functions. The goal is to estimate all those coefficients to recover this 2D surface. So once we have the 2D surface at any new location, you are able to have a spatial prediction. So then when we read the literature in the deep learning, actually from coordinates to basis functions is equivalent to embedding layer in deep neural network. So in deep learning, this from coordinates to build basis functions is equivalent to I use the D to K embedding layers in the network before we pass the data to the hidden layer. Just a few words about basis function. Probably many of you already know the basis functions are elements for function space and can represent any continuous function in the space. It include basis, like for example, Fourier basis, radial basis functions. In this work, we choose a multi-resolution, compactly supported one-line radial basis function. So basically, we start from a very rough grid. We put basis functions like a bump at the node point at this one layer. Then we make it denser. We put another set. We make it denser and denser, hopefully to cover this spatial region nicely. Then the shape of this basis function is controlled by a skew factor that is associated with node spacing. Okay, so this is the structure of deep Kriging. Coordinates are here. So before, the traditional method typically use this together with all the features or covariance as an input. So what we did is before passing the coordinates to the deep neural network, we built a embedding layer which contains all the spatial basis functions. Then this deep neural network actually does regression on covariance and spatial basis functions. So I think the fundamental idea of deep Kriging is to transform spatial prediction problem to regression problem by making good use of this basis functions. Okay. For uncertainty quantification, the deep Kriging in the first paper I mentioned at the very beginning, we proposed to use a histogram to approximate predictive distribution. So for Kriging, basically, if you have a Gaussian process, the point prediction is conditional mean, and then the uncertainty typically is quantified by the conditional variance, because we assume Gaussian, the predictive distribution is a Gaussian distribution. So here, we don't have a Gaussian process as an assumption. So the predictive distribution, we use a kind of non-parametric way to approximate it. So we use histogram. Basically, we introduce the bin, then it becomes classification problem, then to approximate this predictive distribution. So as you can imagine, this method is very sensitive to the bin selection. So later we also developed bivariate deep Kriging and space-time deep Kriging. We chose to use a resampling-based method for uncertainty quantification. But the first attempt that works actually for the first project, we use histogram as approximation to the predictive distribution. Then once we have that, we can use the quantiles to quantify the uncertainty of the point estimation. Okay. In the paper, we have proved that deep Kriging predictor generalizes Kriging by allowing for non-linearity in basis functions and observed features. I think this deep neural network, the real advantage is this non-linearity. Because many times, because for convenience, this linear predictor we use in many scenarios. But this deep Kriging works best if we have a lot of data, and the best predictor actually is non-linear. We also discovered, especially you have a non-linear mean, the deep Kriging works even better than the Gaussian process, than the universal Kriging. In terms of the name, I think induced Kriging is commonly used as the name of spatial interpolation. In the literature, we realize in deep neural network, you have to propose a name. So they actually will propose this name, DeepKriging. I think it was a successful story because later people start to refer this algorithm as DeepKriging. The idea is very simple, basically basis function. That's about DeepKriging. Then later there's many extensions based on this idea. Also, recently I heard one talk in Bayesian deep learnings. They try to do the calibration to make this deep neural network to simulate the data for the model you are interested. So over there, they also showed if you are able to use basis functions, you can capture the spatial dependence much better. Okay, so in the context of Bayesian learning, we follow the argument in the classical literature. We have shown that the associated variance function of DeepKriging falls into commonly used classes of spatial covariance functions. So typically in Bayesian learning, you put some prayers for those bears and the weights, and to say this neural network implies certain covariance functions under those prior assumptions. So we also follow the argument to show the DeepKriging falls into commonly used classes of spatial covariance functions. So DeepKriging can be viewed as a tailored DNN for spatial prediction. So our focus is to propose framework because we are not expert to develop a new architecture for neural network. So we propose this idea basically can be used for other machine learning models developed for regression. So if these models are successful for regression, now you have spatial data which are spatially correlated. One idea is to introduce these spatial basis functions. Then machine learning and deep learning method can be used for spatial data. Such quickly, I show some numerical results. So the first one, I simulate from a Gaussian process. Mean zero Gaussian process. So we know Gaussian process, the best linear predictor is the best predictor. So before we tried many times, we want to show that DeepKriging is better than Kriging. But later we realized because this is the best predictor, in this case, we want to show DeepKriging can do as well as Kriging. So here, as you can see, those dots are the observed value in 2D from this Gaussian process. And the blue line here, I call it a DNN with intercept. So that means we don't consider any covariance, just a DNN on the, consider any coordinates. And the DNN with the intercept and coordinates, that's a traditional method, use longitude and latitude as a covariance. And this red line DeepKriging is our method using basis function. And the last two are the Kriging with parametric covariance functions. So I assume a maternal covariance function or exponential covariance function. Well, first estimate unknown parameter in those covariance functions, then do the Kriging's spatial interpolation. So as you can see, the DNN with intercept and the coordinates only, not as good as a parametric method and DeepKriging. Yeah, because it's basically follow the data. Yes. So the DeepKriging and the other two follow the data very well. Yeah. So the second kind of toy example, we simulate from a non-linear mean function. So this is not a very realistic spatial realization, but we just want to show if you have a very non-stationary feature in the spatial case, and this is a DeepKriging prediction based on tenfold cross validation. The error is smaller, variability is smaller. This is a baseline DeepKriging using coordinates, and this is a Kriging by assuming Gaussian process. So computational advantage, because many deep neural network, these algorithms, they have a pretty efficient implementation on GPU. So we also tried some scalability experiments. So the x-axis are the number of locations, so we call it problem size. And the right line here is the Kriging. The green line is deep Kriging on CPU, and the blue line is deep Kriging on GPU. So because of the more efficient implementation, the deep Kriging using deep neural network on GPU has a better scalability. So for one quick application for spatial data, so here I consider monitoring the sites in the US. So I have 604 locations, they are sparse. On those locations, I have PM 2.5 concentrations. So typically the air pollution data, yes, like this. Yeah, those are the observations here. Yeah. And I also use North American regional real analysis data to extract some meteorological variables as covariance, including temperature, wind, those meteorological variables. Because the real analysis data, they are gridded data. So the resolution is about 32 by 32 kilometers for the whole US, about 7,706 locations. So we want to predict the PM 2.5 concentrations at unmonitored locations. Because we know the health standard is 12 microgram per cubic meters. So we also estimate the probability of PM 2.5 above this health standard. It's a particulate matter. It's a very small size of particulate matter. When you breathe, it's gonna have a more health problem. Yeah, those things like dust is a little bit like PM 10. 10 is the size of the, yeah. So there are a lot of studies about the health of PM 2.5 to the health problem. Yeah, for spatial prediction environmental problem, that's a very important application because it's very hard to predict. It's tend to have a local hot spot, and sometimes it depends on wind direction and the temporal dynamics. So that's why many applications we go for the air pollution. Okay. So this is the data for the US, and the picture B here is a deep Kriging in spatial interpolation, and the D is the classical Kriging by assuming Gaussian process. So as you compare these two, they are pretty similar, but for deep Kriging, we do have more kind of local features from the spatial interpolation. Because we are able to evaluate the probability above the health standard, we can give this sort of like the risk map of PM 2.5 to quantify the high risk regions. Okay, so here is then because we have this leave out locations to do the validation, and we use different metrics, mean square prediction error, absolute error, and classification accuracy to compare deep Kriging baseline DNN with coordinates only and the Kriging. For deep Kriging, we have a smallest errors. So this is a I think if you have experience about spatial prediction, you will notice many times for real application, it's very hard to improve the spatial prediction because oftentimes we develop new models, non-Gaussian models and non-stationary models. But when we come to prediction problem, the value very much depends on the neighborhood. So typically the spatial prediction problem, this error improvement is very, very small if you have a new models. But for this deep Kriging, I was surprised that for application, actually it's very easy to show we have a much smaller errors. I think because for real data, there's no true process. So typically in simulation, you simulate from Gaussian process, stationary, non-stationary, all kind of well-studied class of models. For application, the deep neural network works much better. Right, just a quick summary before I move to space-time. So the deep Kriging is a spatially dependent DNN, deep neural network, with a direct link to Kriging. The uncertainty quantification in this work, we use a histogram. Actually, the methodology is called deep distribution regression, was also published a few years ago. So the Bayesian representation and the we show it corresponds to a Gaussian process. This deep Kriging can be viewed as a tailored DNN, so it's compatible with a wide range of machine learning models for regression. When we have a space-time data, so before I only talk about spatial data, the interpolation actually is very easy to extend to space-time setting. So what we did is, instead of spatial basis functions, we did spatial-temporal basis functions as an embedding layer. Over there, the initial idea for this project is to study whether we can find a better embedding layer to improve this spatial-temporal interpolation. We tried many ways of building this embedding layer, but eventually, when we stack purely spatial basis function and a purely temporal basis function, the deep neural network works the best. We tried also tensor product and everything. It's computationally more expensive, but it didn't really help very much. So actually, the embedding layer in this work is very straightforward. We stack purely spatial basis function, purely temporal basis function, and let the deep neural network to choose which basis functions are important in terms of interpolation. For the forecasting, as I said, because it involves extrapolation, the basis function wouldn't work very well, as you can imagine. So we studied another network, is a long short-term memory, LSTM. Probably you heard many times this LSTM has a good performance in terms of sequence prediction problems. LSTM is a variety of RNN, is recurrent neural networks. So in statistics, I know some work they study LSTM using model-based methods. It's sort of equivalent to state space models in time series analysis. So although LSTM is highly effective for capturing temporal dependence, it does not use information from other locations. It's a single time series forecast. So because we have space-time data, we propose a convolutional LSTM. So basically, we include data from neighboring locations by passing a CNN layer as the input to the LSTM. So LSTM is traditional time series forecasting algorithm. So before that, we add one convolutional CNN layer to include the observation from neighboring observations. Another new thing in the space-time deep Kriging is a loss function. For deep neural network, I think usually the important thing is the loss function and the activation function. Right? So in the spatial case, we consider this mean square errors, loss function mean square errors. So in this space-time deep Kriging, we change the loss function to quantile-based function. So if you are familiar with quantile regression, this loss function you've seen many times. This is in quantile regression is so-called a check function. So tau is the quantile level, and as you can see, if tau equal to 0.5, this loss function reduces to absolute value of this argument, this input. So this check function basically provides a kind of an L1 loss in the neural network. So by changing this tau, we are able to have the forecast for different quantile levels. So once we have a set of quantile levels, we can provide the predictive distribution. So that's the goal. Because we know in quantile prediction, for higher level quantile levels, the quantiles should be larger than lower level quantile levels. So we also modify or propose an activation function for the output layer to avoid the quantile crossing. So the proposed two new methods, we call it a Q-LSTM. That's actually quantile LSTM. And the Q-conv LSTM is a quantile convolutional LSTM by adding one CNN layer to consider neighboring locations. Yesterday, Mark presented actual geostat. If you attended his talk. We developed this actual geostat. We are able to simulate the exact Gaussian process on large scale. So we run computations in the past 3 years, I think. So we participated in 2022 competitions for the space-time setting. So in that year, we had there were 20 research teams worldwide registered, and our proposed space-time DeepKriging won the computation for 100K and 1 million space-time locations. So at the beginning, I was a little bit surprised because I know the true data are generated from Gaussian process. So the DeepKriging Gaussian process should be the worst case for DeepKriging. Then later I realized because it's a large data set, many methods they are not be able to do the exact computation. So the estimation, prediction, they all have some errors. So maybe I think that's one of the reasons this space-time DeepKriging works better in terms of prediction. So the competitors include Vickers approximation. So the GPGP package, later I will also show some simulations. GPGP package is R package developed for Vickers approximation for Gaussian process. So Vickers approximation, roughly speaking, is when you build this log likelihood, instead of conditional on the full path observations, you only consider conditional on nearest neighbors. So by doing that, this covariance matrix becomes much smaller. So this GPGP package participates in all the 3 competitions. Every time is among one of the best top performers. So I think this Vickers approximation, if you have a Gaussian process, is one of the best approximation method. So we are happy to do a little bit better for GPGP package. I think because the GPGP package is best for spatial case, but for space-time, there's a lot of room to improve. So I will give some numerical results we can discuss a little bit in the simulation here. So in this simulation, we compare space-time DeepKriging with GPGP. So, and we also compare with traditional time series forecasting method using single time series ARIMA, this convolutional LSTM and the QLSTM, and the GPGP package based on Vickers approximation. So here I just pick a random time point, show the spatial interpolation from the GPGP package, and this is space-time DeepKriging spatial interpolation. Visually, they look quite different. I think because GPGP by default, you conditional on 30 nearest neighbors, because more than 30, the computation is just much higher. So they recommend a condition on 30 nearest neighbors. I think these very local patterns, possibly due to the not enough neighbors. And another thing I noticed is because Gaussian process, if typically you need to select a parametric class of covariance functions. For spatial case, typically we use Matern covariance functions with 3 parameters, already flexible enough. But for space-time, it's much more complicated because you may have spatial-temporal interactions. This interaction may be symmetric, it may not be symmetric. So if you choose a very simple or not realistic spatial-temporal covariance functions, then will give you a kind of worse spatial prediction. So I guess that's why for space-time DeepKriging, the advantage is more than spatial, purely spatial case. So this right here is I just plot the length of the prediction bound, so you can see the uncertainty in 2D. The darker means more uncertain. Here is one illustration of the forecasting at a specific observed locations. The black dots are the simulated data, and the blue lines are the fitted values. And this gray area are the quantile forecasting based on 90% coverage. And this red line here are the median-based forecasting. So from the simulation, the performance is pretty well. In terms of application, I will talk about air pollution again, but this time a different data set because we are able to handle space and time, not only spatial only. So the period I consider is from January 1998 to December 2022. The time resolution is monthly. I have a monthly spatial observations, in total about 286 months. Because each month, the available monitoring sets actually is different. So on average, 1,900 spatial observations per month. So some monitoring sets maybe stop working after a certain month. So here I selected 3 months observation: December 2021 and June 2022 and December 2022. The first row shows the original observations, and the second row shows the spatial-temporal interpolations. So as we can see here, for example, in June 2022, this region, for that month, we don't really have much data, but the interpolation shows some little bit higher value in yellow. We went back to check the time series. Actually, the high value actually from temporal observations from the past. So that means the spatial-temporal DeepKriging does take advantage of these temporal observations as well. And the last row shows the length of prediction prediction intervals. So for forecast, here I use quantile convolutional LSTM. I pick the first 3 months, January, February, and March in 2023. And this is the prediction interval based on quantiles. Just to visualize it a bit better, I pick one location for San Francisco. I show the probabilistic forecasting with a 90% forecast interval for the final 5 observed months of 2022. So in this plot, for San Francisco, the black dots are the original observations, and the light blue is the fitted value based on 50 per median. 50 quantile is a median. And this dark blue lines are the interpolated value. And this red line here are the forecast value based on median. And the gray area is a 90% interval. So because we left out these 5 observations for validation, so as for comparison, actually the prediction works pretty well. Okay, so in terms of computational time, for the PM2.5 data with more than 200K locations, space-time DeepKriging costs about 7 minutes on GPU, about 19 minutes on standard 16-core CPU. With GPU capability, obtaining quantile for a single location took about 1.5 minutes, 1.37 minutes for quantile LSTM, and about 12 minutes for quantile convolutional LSTM. So in comparison, the GPGP package, as I mentioned before, is based on Vickers approximation. So you need to decide how many neighbors to include for likelihood approximation. It requires 70 minutes with 13 years neighbors. If we change to 19 years neighbors, the computational time increases dramatically to 1.7 hours. It was computationally infeasible with more neighborhoods. Okay. So just to conclude, the DeepKriging and the space-time DeepKriging provide a novel framework for spatial and spatial-temporal interpolation and probabilistic forecasting. It is suitable for non-Gaussian processes because the best predictor may not be the linear predictor, and non-stationary process. Although, as I mentioned before, in our simulations, at beginning we tend to simulate Gaussian process, non-Gaussian process with 0 mean. We observe the improvement, but with very small margin. Then we try the non-linear mean function. So over there, this deep neural network-based method works much better. Yeah, and the probabilistic forecasting we propose, we call it quantile LSTM and quantile convolutional LSTM. So LSTM is the traditional time series forecasting deep learning algorithm. So the modification we did is to change the loss function to be able to provide a quantile forecast and to add convolutional layers to be able to consider neighbors. So the proposed approach is computationally scalable and can be easily extended to large data sets with minimal hardware support. So with this, I think just one, if I use one word to summarize this idea, is use a basis function or loss function we are familiar with to improve the deep neural network. Our focus is spatial prediction, spatial temporal interpolation and forecasting. With this, I will stop here, and I'm happy to answer any questions you may have. Thank you very much.
Any question?
Thank you for your talk. I think maybe I missed the main point, because you have this spatial basis that you use instead of latitude and longitude, right? But do you give it to this basis function to the network, or the network construct this basis function for you? This
I give to the network.
I give to the network.
Yes.
Which functions are them?
I use this multi-resolution Wayland radio basis function. So like for example, if we do non-parametric regression for 2D case, there are different ways of providing 2D basis functions. I think those basis functions all will work for this neural network. So I think the idea is very similar to non-parametric function estimation. So when we do non-parametric regression, we need to pick like basis functions first, right? Then we estimate those coefficients in front of those basis functions. I think this deep neural network has their way to actually estimate the neural network by this bias and the ways in a nonlinear way. So that's my understanding. I think if I think about statistical estimation and deep neural network, I think the closest is a non-parametric regression. Yeah, because the classical deep neural network, when they deal with spatial data, they don't explicitly consider spatial dependence. So then the information is not very efficient if you use very highly correlated predictors. I think basis function in that sense works better. And also, once we have this framework, we can go back to the statistical framework to be able to provide predictive distribution. We can talk about these uncertainties as well. Yeah, thank you.
Any other question? I have one. Does space-time DeepKriging deals reasonably well with missing data? Because here in Brazil, when you look at environmental data such as wind speed, temperature, there are entire holes of missing data on a substation. Does it?
Yeah, I think can be used for imputation, because here we use the DNN, deep neural network, because we have irregular spaced locations, also in time, not necessarily. If you have missing data, you can also think of as irregular spaced locations. This space-time, I didn't explicitly mention, space-time DeepKriging actually the two-step procedures. The first step is to do imputation, basically. Okay. Yeah, so once you have a complete data set, where you do the convolutional neural network, you have neighbors to look at. Yeah, the imputation can be, I think this also can be used for this satellite gap filling. When you have the satellite data for environmental data, many times because this orbit, you have this gap from the data. I think I've seen many Kriging-based methods used for impute all these missing values. I think space-time DeepKriging can be a fast way actually to impute all those missing values. Yeah. I think the data larger, the better. When we want to show in the simulation, we have to simulate enough data I think all the problem is the same. For deep neural network, if you have more data, they perform better. Yeah. Thanks. Yeah. Yeah. Thank you.
More questions?
Thank you very much for the presentation. I was just wondering, is there a way to sort of incorporate some physical knowledge about the system in the neural networks in the similar way that pins do this job, physically informed the neural networks? And do the basis functions sort of help you to sort of create a non-linear finite elements method or something? Is there a connection to be made there?
I think it's a good question. I think yes. We never done that before, because in spatial modeling, I know there's a big area is a physics kind of motivated statistical modeling. Usually in these linear dynamic models in Bayesian analysis, they have a because they know the Earth system and it's physics. With the model, you can incorporate some information. I guess those things, if can be treated as a predictor, we can better use those predictors for the deep neural network. My understanding is probably limited understanding. This deep neural network is really good for predictions. So, but it's for regression problem. So if we have knowledge, we can provide a better regressor or better predictions. Then this nonlinear forecast, nonlinear prediction will work better, have this more flexibility. So if we have knowledge, we can do this better, I think. Yeah.
Okay, thank you for your talk. Is any possibility of making inducing some sparse models where you have some coefficients equal to 0, or in putting some regularization to have more sparse models?
I think it's I'm not expert in this, but you are right. This deep neural network, one area of study is to study the regularization. Here they have, for example, they have this dropout, random dropout. This is to prevent this overfitting. So it's sort of implicit. I mean, regularization in terms of regression variable selection, for example. I think the deep neural network that can do the regularization, but not in a very clear way of variable selection. So my experience is, I have some other projects that they talk about explainable AI. So basically, they have the algorithm to see which regressors are important. For me, it's just our variable selection problem. I don't study this, but I think the neural network, for example, the first one, we did a dropout. But later we realized, well, is the observation not very noisy? It seems not very necessary. Yeah. But one of my collaborators, he proposed some potential directions to think about it. This neural network, can we formulate as a panelized regression problem, as you mentioned? Yeah. Thank you.
So thank you very much for your talk, and we have coffee break here.
Thank you so
Thank
much.
you. Obrigada a todos.